Yeah. Yeah, other people are Jean-Olivier. You may remember Shruti. Jean-Olivier is also against the team. So thank you for joining the club.
Actually, can't. I think you're probably seeing yourself now.
No,
I'm like too afraid to stop sharing. So how do we do questions here?
So I think you can ask questions anytime.
Okay.
You can ask. Yes, you as being everybody who is listening can ask questions anytime.
Okay, so
is that okay for you?
No, that's fine. But like, so I would prefer if they just stop me and just interrupt and ask questions rather than me looking at some raised hands or something. Yeah.
So what will happen is that if so I'll pay attention to this. I will look at the hands, and if someone wants to ask a question, I think they can unmute themselves and do it. If they're not comfortable, they can type the question and I can ask, or they can raise their hands and I can go ahead and stop you to make them. I mean, make them whatever works. But you won't have to pay attention to that.
Okay, sounds good.
I might close my camera to preserve the bandwidth once the talk starts. So if people are joining, I will wait. We're exactly at the hour, so we'll wait 2 minutes more.
It's good to see familiar names.
Yeah. So when were you in Shabbat last time?
2018. I was there for was it 2018 or 19? I think 19 was that conference, right?
The quantum cavity workshop.
That's right.
Which has been, we've decided to postpone by 1 year now. It should have been this June 2021. Okay. But yeah, with that much uncertainty, we decided to postpone to 22.
Right.
So it will be the 6th edition.
Okay.
Okay, I think we can. Oops. Okay. Yes. More people joining. I think we can probably start. There will be more people joining, but we should go ahead if we want to keep the time. So, well, thank you very much, Shruti, for accepting to give a talk here. So many of you, Shruti, very well. She was after her PhD with Yamamoto in Stanford. She was a postdoc in Sherbrooke from when to when? Help me remember.
2014 to 17.
Okay, I knew that. And she then joined Yale as a postdoc. So when in Sherbrooke and continuing on to Yale, she really developed new directions that had quite a bit of impact in the field. Well, I won't steal all of the points, but different ways to make qubit with interesting properties, in particular in the context of quantum error correction. And so since this spring now, she is now a faculty member at Yale in physics or applied physics?
Applied physics.
Applied physics, and affiliated with the Yale Quantum Institute. So we're extremely happy to have her with us today. Hopefully next time it will be in person, but at the moment, thank you for taking the time with us on Teams. So with that, I'll let you go.
Thank you, Alexandre. for inviting me and giving me the opportunity to return to Sherbrooke, and even if it's virtually, and update you guys about the research we've been doing. And the topic that I'm going to talk about today is essentially started in Sherbrooke while I was a postdoc there. So it's now returning back to, the updates are returning back to Sherbrooke, I guess. Okay, so today I'm going to talk about how to build fault-tolerant, scalable, quantum error-corrected computers using qubits, kind of qubits, which are encoded in oscillators. Before I jump into the talk, I would like to list all the collaborators. Of course, it's a long list. I couldn't list everybody, just the main names. Of course, Alexandre's group, there's so many people involved in this project from time to time that it's hard to list everybody. But I would like to mention Alexandre's master, Luca, who was Alexandre's master student at that time when I was there. And he had a very important role in, while we were developing some of the important ideas that go into what I'm going to talk about today. I would also like to mention that recently, what I'm going to talk about, there are experiments being done to realize that, and I think Alex Grimm may have spoken in Sherbrooke, I think last year or maybe earlier this year, I don't remember, but I think he did give a talk about some aspects of this in Sherbrooke. And now,
Alex was a postdoc, PhD student with Max Alfine, in fact, before. So.
Okay. I did not appreciate that. Okay, cool. Awesome. Okay, so also Nick Frattini, who is a PhD student here, is continuing the experiments. Okay, so there are going to be two main messages to my talk. The first message is that for a long time, we have considered fidelity as the sole metric to define how good, or to characterize how good or bad your qubit system is, or how good or bad your gates are. But what I want to tell you today is that fidelity is not, it should not be the sole metric to characterize your system. What is equally important metric is at the structure and the noise, or what I'm going to explain, the bias and the noise. So basically, if I give you two qubit platforms where the total fidelity or the total infidelity of all the operations is the same, but in one case, one qubit platform has structured noise, whereas in the other qubit platform, the infidelity is basically equally distributed into different types of errors, then it's much more beneficial in terms of error correction to work with the first system, which has structured noise. The second message is going to be that fault tolerance with bosonic qubits is not only possible, but much more efficient. So bosonic qubits are qubits that are encoded in oscillators. And so the idea of having bosonic qubits is not new. It's been around for a while, but it was not very clear on how to scale it up and truly make it a fault tolerant system. But with some of our recent work, we now know how to scale these bosonic systems up and not only make fault tolerant error correction possible, but make fault tolerant error correction much more hardware efficient. So I'm going to give you some numerical evidence of this statement with the example of surface codes implemented with these bosonic Kerkat qubits. So with that motivation, let's come to the outline of the talk. So I'm going to start with the basics. I'm going to tell you about what I mean by structured noise. You're going to look at the surface code, a really fast, quick introduction to the surface code. Then I'll tell you about these bosonic cat qubits, and then I'll tell you how you can get high thresholds with the surface code made with cat qubit. So let's start with the basics. So when you describe a quantum system, you typically decompose errors into three kinds of errors. You decompose it as a bit flip error or an X error, which is like the action of a poly X operator on your state. So 0 goes to 1, 1 goes to 0. There's a phase flip error, which is like the action of a poly Z operator on your state. So you basically pick up a -1 sign between the 0 and 1 state. So you mess up the phase information. And then you have the Y error, which is the combination of both X and Z errors. So you not only cause a bit flip, but you also cause a phase flip. Now, in most of the studies on error correction codes, people look at a depolarizing noise model. That is, we assume that all errors X, Y, and Z are equally likely. So the probability of a Z error is same as the probability of X error and is same as the probability of a Y error. However, in many realistic qubit platforms, this is actually not the case. And in many cases, what happens is that one error dominates over the other errors. Such systems are called as biased noise qubits. And the one particular biased noise qubit that we're going to look at has X and Y, has the probability of X and Y errors exponentially suppressed compared to the probability of a Z error. So when you talk about biased noise channel, in addition to the total probability of error, which is Px plus Py plus Pz, we also need to look at what is the bias. That is, what is the ratio between the probability of a Z error and the probability of X and Y error. So this quantity bias is going to be important. So when we want to build an error correction code to correct for these X, Y, Z errors.
Sorry, Shruti,
yes.
I have a question. If you could go back to the previous slide.
Yeah.
So the Y noise is it can be seen as a combination of X and Z. So it's not independent from X and Z. So why not consider just X and Z noises?
Well, that's a great question. It actually depends on your system. So in some cases, you have uncorrelated noise. So you have uncorrelated X and Z noise, which means that the probability of Y noise is just probability of X times probability of Z. But in many systems, that is not the case. You do get independent Y noise as well, in which case the probability of a Y error is not just a product of probability of Z and X error.
Okay, thank you.
Yeah. Okay, so when we talk about error correction, we not only want to correct for these X, Y, and Z errors happening on the qubits, but we also want to correct for errors that can happen during the gate operations that you do between these qubits and also during the measurements. If your error correction code is able to correct for all such errors, then it is called as a fault-tolerant error correcting code. Now, the important, one of the main challenges that can happen for errors during the gates is that the gates, especially the entangling gates, can spread errors between different qubits, and it can also change the nature of errors. So just to give you an example, if you look at the C0 gate, which is a 2-qubit gate between a control qubit and a target qubit, it is a very important component in error correction codes. What this C0 gate says is that if the control qubit is in the state 0, don't do anything to the target qubit. But if the control qubit is in the state 1, then flip the target qubit. In this case, the symbol for the control NOT gate is like so. So if there's an X error on the control qubit, you see that it spreads or propagates as 2 X errors, one on the control and one on the target qubit. So it is very important that your error correcting circuit is able to correct for circuit level noise as well. If your circuit can do that, then it's a fault-tolerant error correcting code. And with this, the advantage is that you can reliably execute an arbitrary length quantum circuit with unreliable parts, as long as the error per gate operation or per time step is below a constant value, which is called as a threshold. Now, for the condensed matter theorists in the audience, I would like to emphasize that there's actually a deep connection between error correction and statistical mechanics. So you can actually map the noise in the quantum code to disorder in an equivalent stat-mech system. In this case, the quantity threshold becomes corresponds to a phase transition in the equivalent stat-mech system. So basically, if your system is correctable, that is, it's below threshold, then the stat-mech system will be in an ordered phase. And if the errors become too high, that is, the error rate is above threshold, then your stat-mech system goes into a disordered phase. So this phase transition between the ordered and disordered phase actually tells you what the threshold of the quantum code is. And that fact, this is very important, and a lot of thresholds for the topological error correction codes actually have been calculated using this mapping. In addition, the optimal decoding in the quantum code actually is equivalent to calculating the partition functions in the StatMech system. So I always like to make this analogy. I think it's a beautiful analogy, and you know, to also keep the condensed matter theorists in the audience interested. Okay, so now we'll look at a very popular fault-tolerant error correcting code, which is a surface code. So you guys are familiar with it, but just so that we're all on the same page, let me give a quick recap. So in the surface code, the qubits are arranged in a 2D lattice. So this is a patch of the surface code. The white circles are the physical qubits, and this patch basically makes a logical qubit. So in the surface code, you detect errors by measuring two types of stabilizers. The stabilizers are the X-type stabilizers and the Z-type stabilizers. The X-type stabilizer is a 4-body X operator acting on the 4 qubits around the blue plaquettes. And the Z stabilizer is the 4-body Z operator acting on the 4 qubits around the red plaquettes. And then at the edges, you have the 2-body X and Z operators. So basically, if you can, if there's a Z error, if there's a phase error or a Z error in your qubits, then that error anti-commutes with the X stabilizers, and you can use that to detect for Z errors. And there's an X error in the circuit, it anti-commutes with the Z stabilizer. So by measuring the Z stabilizers, you can detect for X errors. And if there's a Y error, then both X and Z stabilizers will tell you about it. And you can then also decode the Y errors. Now the size of the patch you need is depends on how many errors you want to correct. So if you want to correct n errors, then this is a 2n plus 1 by 2n plus 1 patch. Now if the physical error rate is p, and I'm assuming a depolarizing noise model, so all of these errors are the same, then the threshold for the surface code is about 1%. What it means is that the probability of a logical error, the probability of having an error on a logical quantum bit of information stored on this lattice decreases exponentially with p over pth, where pth is a threshold. So basically, as long as p is below pth, this value is less than 1, and so just by increasing the size of the code, you will get lower and lower logical error rates. Now, just to give you some sense of how big of a lattice you might need, say you want to factor a 2000-bit number, then the logical target rate that you're trying to reach is about 10 to the minus 12. If the physical error rate is 0.1%, then to reach this target rate, you need about 12, n equal to 12. And so you need, this sized lattice. Now, say if you, magically, if you were able to increase the threshold by a factor of 2 or decrease the physical error rate by a factor of 2, then for the same size lattice, you'll be able to reach much lower logical error rates, which means that now you'll be able to solve on the same lattice or using same size lattice a much bigger problem, like finding the ground state energy of a big molecule like FOMOCO or something. So with this quick introduction, I will talk about the Kirkad qubit, and I'll tell you how you can improve these properties, how you can improve the thresholds of the surface code using the Kirkad qubit. Now, the Kirkad qubit is a bosonic qubit. What is a bosonic qubit? A bosonic qubit is a qubit encoded in two orthogonal non-classical states of an oscillator. So these are typically made in harmonic oscillators. So here is the Hamiltonian for a harmonic oscillator. A and A daggers are the annihilation and creation operators. Why do I care about encoding a qubit in an oscillator? Well, especially in superconducting circuits, the oscillator or the resonator, the microwave resonator, which could be a 3D resonator, has a longer lifetimes. So you can start with lower error rates. And also, we know that we can take advantage of the infinite Hilbert space of this oscillator to actually do some local error correction on the bosonic qubit itself. So this is the sort of motivation behind the GKP codes, CAT codes, binomial codes, and other bosonic codes you might have heard about. Now, the interesting part though is that how do you control the states in a harmonic oscillator? Like you need some anharmonicity, you need nonlinearity to be able to control, to be even able to make a non-classical state. So here, what people use in superconducting circuits is the Josephson junction or a transmon qubit as the external nonlinearity, and they use that nonlinearity to do operations on the bosonic qubit. Unfortunately, however, there are some errors transferred, or there are some errors which backpropagate from your transmon back onto your bosonic qubit. So you sort of lose some of the advantage that comes from the long oscillator lifetimes or direct error correction. So it turns out that there are some errors left behind which you cannot get rid of, and so eventually you still need to put these bosonic qubits in a bigger error correcting code. So you basically want to concatenate these qubits with something like a surface code. So now you can imagine.
Just briefly, Shruti, I don't know, in the previous slide, for those who are not so familiar with these systems, can you just compare the lifetime for oscillators versus like your typical transmon? Just right. So, I mean,
yeah. So the lifetime of like a typical transmon would be what, like 20, 50 microseconds. Maybe in some 3D transmon, it could be a bit better. But the lifetimes of these oscillators can be several milliseconds as well. So there's this huge difference between the lifetime. So you expect that because the qubit in the oscillator is living for a long time, you'd be getting really low error rates, which is true until you bring about this external nonlinear element which decays at 20 microseconds or 50 microseconds. Some of that decoherence from this external nonlinear element actually goes back to your qubit system. So the effective lifetime of the qubit then is sort of limited by this nonlinear. So it doesn't remain 1 millisecond. Unfortunately, it decreases slightly because of this element. Okay, so now what we want to do eventually is put these bosonic qubits in the surface code. Well, if I wanted to use the surface code anyways, why did I even try to make a bosonic qubit? Well, the idea is that you're starting with a much better qubit. You are able to do some local error correction or give some local protection to your qubit. Even though if it's not full protection, it is still better than just using a regular qubit by itself. So the P that goes into your formula to begin with is going to be smaller, and so you're going to need a much smaller lattice to reach the same logical error rates. Now the other question that we wanted to answer was, can we actually, so your regular harmonic oscillator qubits are basically, the idea is that you reduce P, but the question that we wanted to answer was, can I increase the threshold for the surface code using bosonic qubits? And it turns out that the answer is yes. And for this, we're going to use a very special bosonic qubit, which was, we started to work on in Alexander's group, which is this bosonic Kirkat qubit. The Kirkat qubit is a very interesting paradigm, because what you do here is that, remember, this was the bad element, that this Josephson junction was the thing that was backpropagating errors onto your oscillator. But once you realize that this Josephson junction itself is an oscillator, but a nonlinear oscillator, then the question is, can I use this nonlinear oscillator and encode a bosonic qubit, so that now I don't need another external nonlinearity to control that bosonic qubit. So now you basically make the system more compact and more efficient. So that is the idea of the Kirkat qubit, that it is a bosonic qubit realized by some sort of driving of a nonlinear oscillator, and it still retains the properties, it still retains the good properties of the bosonic qubit, but it also gives you the ability to efficiently control it without requiring external things. So let's quickly look at what this bosonic qubit is. So if you look at the Josephson junction, the Hamiltonian can be approximately written in this form. So the first term is the frequency, and the second term is the Kerr nonlinearity. Now what we're going to do is drive this system with two drives, which are equally red and blue detuned from the center frequencies. So you'll take one photon from this drive, one photon from this drive, and because of this fourth order nonlinearity, you will convert it into two photons at omega q. So you get this two photon drive here. This is just a frequency term, so this is just your frequency, and phi is the phase of the drive with respect to some clock phase. Now it turns out that in superconducting circuits, there's another element which you can use, which is called as a snail. It's basically, in the snail, you basically replace a single junction with four junctions in an asymmetric fashion, and you flux bias it in such a way that you not only get a four-wave mixing, but you also get an additional three-wave mixing. So because of this additional three-wave mixing, now you just need to apply a single drive at the center frequency to get the two-photon drive. Okay, so once you get this two-photon drive, you can now go into the rotating frame, and in the rotating frame, you lose all the frequency terms and you get a time-independent Hamiltonian. Now, this is where the magic happens. Now, what you can do is you can factorize this Hamiltonian and write it in this way. This is exact factorization. We didn't do anything strange to it. Now, I'm going to substitute alpha equal to the square root of these guys over here so that the Hamiltonian looks like this. Now, you'll immediately see that there'll be two coherent states plus minus alpha, which will be destroyed by this term. That means that the two coherent states plus minus alpha are the degenerate eigenstates of the Hamiltonian. That means that even in odd superposition states, which are the cat states, are also the degenerate eigenstates of the Hamiltonian. So lo and behold, we have created a driven system whose eigenstates are the cat states, in which I will want to eventually encode my quantum information. So we can have the even superposition cat state, which is alpha plus minus alpha. And if you look at the Wigner functions, you'll see there'll be two blobs at plus and minus alpha with the fringes at the center, and there'll be a positive peak at the center here. And for the other superposition state, alpha minus minus alpha, the Wigner function looks like so. And in the interference fringe here, you see a negative peak at the center. These two are exactly orthogonal states, and I can use that to encode a bit of quantum information. Now, this phase phi is a free phase I can choose. It's just the phase of the drive with respect to a clock. And this actually becomes useful when I do a C0 gate between cat qubits. But right now, forget about this phase for a second, and we will define the cat qubit with the phase phi equal to 0. Okay, so now, as I said, we can encode a cat qubit, and this is the block sphere representation I'll be using. So the cat plus and cat minus states are along the x-axis of the block sphere. They're superpositions, which are, so the even and odd superpositions of the cats are approximately the coherent states, which are along the z-axis, and the other superposition is along the y-axis. So in this block sphere, the Pauli z operator is basically just flips you between C minus and the C plus states, whereas a Pauli X operator just puts a phase between the C plus and C minus states. On the right-hand side here, I'm showing you the Hilbert space structure of this driven Kerr system in the rotating frame. So in the rotating frame, the cat plus and cat minus states are exactly degenerate, as I've shown, and the rest of the Hilbert space is detuned or is separated from the cat subspace by an energy gap. This energy gap increases with the nonlinearity and basically how hard you pump the system. And this is the nonlinearity which actually allows me to define the qubit. This is the energy gap that actually allows me to define a qubit, because now I can apply a drive selectively at this frequency and cause transitions between the cat plus and cat minus states without ever leaking out to the other states. So the bigger this gap, the faster I can do the gate operations. And in superconducting circuits, this gap can be as large as 2 megahertz, which means that you can do fast gate operations, which is about 100 to 1,000 times faster than the typical decoherence times in the system. Okay, so now I've been telling you that this is going to be a bias noise qubit. So I have to tell you how this system couples to the environment and convince you that this is indeed going to be a bias noise system. So for any coupling of between this qubit and the environment, I can write it in this form. This is like a general expression. A and A daggers are the annihilation and creation operator for my cats, and E is just some coupling term of the environment. It's just some operator of the environment. Now, so we have done some detailed derivations in our paper, but I'm trying to just give you a more intuitive, hand-wavy picture of why this is going to be a bias noise qubit. So now what we're going to do is we'll take this operator and basically just sandwich it between the cat plus and cat minus states. When I do that, I'll see that when I sandwich this between the cat plus and cat minus states on either sides, then this term basically, this matrix element basically increases polynomially with the size of the cat, with alpha, right? So that means that this operators is able to, this coupling to the environment is able to couple between the C plus and C minus states, and the coupling, the coupling between C plus and C minus state is like coupling to the poly Z operator of the system. And what this is saying is that the coupling along the poly Z axis is increases polynomially with the size of the cat. Okay. Now, yeah, so basically you can write A dagger MAN as poly Z. But now I have to tell you that the coupling to the other axis, like the X axis, is going to be exponentially suppressed. In order to do that, I'm going to give you a qualitative analysis for which we will go into the, we will look at the semi-classical picture. We'll look at this Hamiltonian in the semi-classical picture. So in the semi-classical picture, this Hamiltonian actually looks like a double well, in double well structure in phase space, in which the two wells are separated by the size of the cat. So the dips of the two wells actually appear at minus alpha and plus alpha, and so they're separated by 2 alpha. And so, and now you can, if you try to quantize it, you're going to get, different energy states here. So the lowest energy states are actually our coherent states, and the minus alpha state and the plus alpha state. Of course, in the quantum regime, you can have them exist, as cat states, that is, as a superposition of these two coherent states. Now you see that poly X operator means that I need to go from minus alpha to plus alpha and plus alpha to minus alpha. This is what poly X needs to do. Now there are two ways that this can happen. One is you can try to tunnel under the barrier to go from the left to right and right to left. But tunneling under the barrier is actually exponentially suppressed because of this height here, which also increases with the size of the cat. The other thing you could do is you could try to hop over the barrier. You also need a lot of you need to jump up many times. You need to go through all these levels to actually hop over the barrier. So it turns out that in order to hop over this barrier, you actually need a very high order coupling with the environment. So you need a coupling like this, where M is related to how many levels are actually inside this barrier, and that increases with the size of the cat. And so basically any way you try to any way to go from the left to the right of the barrier is basically suppressed. So we have done more detailed analysis in our paper, and we have actually shown that the X and the Y errors, because of primarily this reason, are exponentially suppressed compared to the Z errors. And this is indeed a bias noise qubit, where the bias, which is the ratio of these two guys here, increases exponentially with the size of the cat. And we can do some analysis, and I'm going to show a more concrete example. And with reasonably sized cats between 5 to 10 photons, you can expect biases between 1,000 to 10,000. Okay, so let me give you a more concrete analysis. So what we did was we took this Kerr-Cat Hamiltonian, we subjected it to some white noise environment. So it had single photon loss, and we put single photon gain in it. And we put some extra dissipation, which is a special 2-photon dissipation. I'm not going into the details of why we put it there right now, but we basically picked up very reasonable, parameters we expect to have in the experiments and get this and simulate this master equation and extract the error channel of my qubit. And I plot these different terms. So you see, if I plot these two terms, which is the probability of no error and the probability of Z error, then the probability of no error, of course, and the probability of Z error increases. As we expect, the coupling of the Z error with alpha has to increase polynomially with alpha. Now, but the important thing is that if you look at any other term, which is not a Z error, so if you look at, say this, which is probability of a Y error, so if you look at all these other terms, they exponentially decrease with alpha. So the decrease in these other guys, is much, much faster than the increase in this in the probability of Z error. So this is why it's a biased noise qubit, and we can use this example to extract biases of up to 10,000 for up to 10 photons. Okay, so now I'm going to quickly tell you what are the different operations we can do on this qubit. I'm not going to tell you all the details. If you're interested, I can talk about it later, or you can look at it in the paper. So the different operations we can do on the system is initialization, which happens adiabatically. You can do a Z theta gate, which is basically just applying a regular microwave drive at half the pump frequency. You can do a X pi over 2 rotation. This is the only operation for which you need to break the symmetry, for which you need to break this double well symmetry that you have. And I'll tell you about the consequences of doing that just shortly. And then you can also do the readout, you can do a Z theta gate, and you can do a control NOT gate. So these are the different. Importantly, you should also look at the noise channel of these gate operations. Remember, the noise channel of the gate operations are not necessarily the same as the noise channel of your idle qubit. So if you look at the noise channel, for these operations, it is biased. For the last two operations, it is biased. But for this X pi over 2 gate, it is not biased because, as I said, you have to break this double well symmetry to do this X pi over 2 gate. And in fact, no matter what you do, we can prove that you cannot do a X pi over 2 rotation in the system. What is remarkable about this qubit is actually the C0 gate, and this is the work. This is a consequence of the work we did with Alexandre, was that you can do this C0 gate in a bias preserving manner. So you might ask, oh, you cannot do an X pi over 2, but you can do a C0 gate, which also needs to have an X, but you're not able to do this in a bias preserving way, but you can do this in a bias preserving way. Yes, we can do it in a bias preserving way, and in fact, the only reason we can do it in a bias preserving way is because this Kirkat qubit is a bosonic qubit. It is a continuous variable qubit, and using this in underlying infinite Hilbert space dimension, we're able to perform a C0 gate in a bias preserving way. You cannot, so if you have a regular qubit, just an ordinary exactly 2-level system, in that system, even if the noise channel of the idle qubit is biased, when you try to do a C0 gate, the C0 gate itself will unbias the channel, and we'll come to this point again. So in an ordinary qubit, you cannot do this in a biased way, and this was the main result of our work here. Okay. So out of these, so I explained why that gate is important. So now out of these things, we have done, well, the experimentalists have demonstrated a lot in experiments, in recent experiments. So firstly, they were able to remarkably initialize these or prepare these Kirkat qubits in their system. So this is what their system looks like. This is the snail device. Remember I told you about the snail? So this is where their cat lives. They made the cat in the snail device. And this is made up of 4 Josephson junctions. And they were able to make, with the pumping technique that I described before, they were able to make cats of about 3 photons, and which implies a bias of about 50. So to really see the high biases that I was talking about, 1,000 to 10,000, you need to go to 4-photon cats. That's sort of where the threshold happens. So we can get there very easily in the next experiment. In that experiment, they were also able to do all the single qubit gates and the readout. So they were able to do the Z gate, the X gates, and the readout. And you see that all these gates, including initialization, are very fast. So the T1, the effective T1 time of this system. So before you pump the system to make a cat, it is actually a transmon. So the effective T1 time of that transmon was about 20 microseconds. So these operations are much, much faster than the lifetime of the system. And as I said, they were able to demonstrate the bias. Sorry, was there a question?
Yeah, I was going to ask something. So you alluded to the size of the cat, which was about 3, and then the next experiment, which would increase. Is it something you can talk about? At least give an idea of. Is there something fundamentally changed to increase this, or is just some little details?
Yeah. So it's both. So in the first, because this was the first experiment, they wanted to be a bit conservative. So they parked their qubit such that it could be used as both a transmon and the Kerkat, which is not a great place to be. You really want to be in the deep Kerkat regime. So because of this, the way the parameters were chosen sort of also prevented you from pumping too much, applying too much pump. But the reason for doing that was because they wanted to do this readout, which was a new readout that they developed, called the quadrature readout, which is what we would want for a cat qubit. But at the same time, they wanted to do the ordinary dispersive readout for the system in the Kerkat, in the transmon regime as well. So that was sort of the interplay of parameters that they had to deal with. So now that they understand the system, they know that the readout works. The theory matched the experiments. So now they're confident and they can really push themselves to be in the deep cat regime.
Okay. Thank you.
No problem. So we can talk more about this later if you want. Okay, so now let's see how I can use this bias noise qubit and the bias noise gates to make surface codes with higher thresholds. So in the last couple of years, just last 2 years or so, a lot of work has been done on tailoring the surface code for bias noise. So these were the two early papers early and some also recent papers that came out on the tailored surface code. But the numerical results that I'm going to show you today is for slightly different surface code, which we call the XZZX surface code. So these surface codes are CSS codes, and this one is not a CSS code remarkably, but it turns out that this has some nice properties, and it's good for bias noise qubits as well. So I'm going to give you numerical results based on this surface code. So the XZZ surface code, unlike the regular surface code, has only one kind of stabilizer. So it has only the one stabilizer, which is a combination of X and Z's. So you have the X, Z, Z, X stabilizer. And at the boundaries, then you just have the two-body stabilizer. So at the boundary here, this will be like the ZX. This is ZX stabilizer, and this will also be ZX, and this will be XZ, and so on. So now how do you measure the stabilizer? Well, you just put an Ancilla qubit at the center. You initialize the Ancilla qubit in some state. You do C0 gates and C phase gates between the data qubit and the Ancilla qubit, and then you read out the Ancilla qubit. And depending on the final state of the Ancilla qubit that you read it out, and you know whether there was an error or not. Again, just this one stabilizer is enough for you to detect for all three errors, X, Y, and Z. So if you look at what happens with the Z error, so say if there's a Z error on this qubit, then you'll see that when you measure stabilizers, this stabilizer will say, okay, I've changed. It'll become -1, and this stabilizer will become -1. If you put two Z errors here, you'll see that this stabilizer becomes -1 and this stabilizer becomes -1. So if you're looking at it, it immediately looks like you're making a repetition code, and indeed that's true. If there was only Z errors in your system, then this XZZ code is actually just lines of repetition code put together. If you look at the X error, then the same thing happens for the X error, but now this repetition code happens on the other diagonal, the 90-degree rotated diagonal. So now if there's an X error here, you'll see that these two guys will say the error, and if you put, say, X error here and here, then these two guys will light up and so on. So basically, the nice property about this XZZ code is that even if you have Z dominant noise or X dominant noise, it looks like a repetition code. So then you would ask me, why not just directly use a repetition code? Why use this weird XZZ code? Well, repetition code works for infinite bias, but this code works for finite biases. So if you have, as I said, if you have no X error, then this is indeed a repetition code for Z errors, and you can just replace this entire thing with one repetition code and you'll be fine. But in a realistic system, our biases are what? At max going to be 1,000, 10,000, that is sort of our optimistic results. So because of that, you still need to have some ability to correct for the less dominant error. Because if you don't correct for less dominant error, those less dominant errors will eventually grow in your circuit and they'll become uncontrollable and completely destroy your logical information. So you need to have some correction for even the less dominant errors, and that's why we use this XZZX code. So what they showed in their in this paper that came out just, I think, a month back, was that with this system, you could actually improve the threshold by a factor of 2 or more for biases greater than a factor of 100 or more. So again, this improvement doesn't come for some unrealistic bias numbers. It's coming from some very realistic bias numbers. Bias of 100. We already have a bias of 50 in the experiment, which is the first experiment on the Kercat, which we were actually surprised to even see these numbers, and we easily expected the biases to be much better than 100 in the later iterations of the experiment. So you might say that a factor of 2 increase in the bias is not that impressive, but well, if you remember this formula, just by increasing the threshold by a factor of 2, you actually exponentially reduce the logical error rates. Now these thresholds here were derived under the assumption of phenomenological noise, which means that you don't consider circuit level errors yet. You're just putting errors on data qubits and you're putting errors on the measurements, but you don't consider the details of the errors that happen in your circuit. So the question then is, when you do these gate operations, so even when you do these gate operations to extract your error centers, what happens? Does something bad happen and prevent me from from improving the biases so much? Well, actually something bad does happen. So let's see what bad can happen. So, okay, so if you look at this circuit, the one thing that you're doing here is a control Z gate between your data qubits and the ancilla. So you will have some sort of a ZZ interaction between the ancilla and your data qubit. If you have a ZZ interaction and your dominant errors are Z, then any Z error during the gate propagates as Z errors after the gate. So Z errors don't change through this gate. Similarly, so the noise channel of the CZ gate remains biased, and similarly we can show that the errors in the preparation and measurements remain trivially biased. So Z error in the preparation or measurement will remain to be a Z error. It will not change its nature. However, the problem comes when you try to do a C0 gate. When you try to do a C0 gate, you'll try to do you would naively try to imagine some sort of an XZ interaction between the data qubits and the ancilla. In this case, if there is a Z error on the data qubit, that actually doesn't commute with this Hamiltonian, and a Z error propagates as a linear combination of Z errors and Y errors. So your C0 gate automatically unbiases the error channel. It is converting the dominant error, which is a Z error, to a less dominant, to an error which was initially less dominant, which is the Y error. So this is bad. So in this case, you would actually not expect to have an improvement in the threshold because you don't have a biased noise channel anymore. In fact, there is a no-go theorem which says that native bias-preserving CNOT gates are impossible in strictly two-level systems. This was first observed in this paper by Alifers and Preskill, oops, sorry. This fact was observed in this paper by Alifers and Preskill, and when we were working with Lucas and in Sherbrooke and continuing in Yale, we realized that we can overcome this no-go results. But I'm going to come to that in a second. Now I want to prove to you, before that, I want to give you numerical evidence that it is very important to have this bias, to have a CNOT gate which maintains the bias to actually see an improvement in threshold. So what we do is we take this XZX code and we simulate the system. So we encode a logical bit of information and look at what is the effective logical error probability, after error correction. If I was given a CZ gate, if I was given the CNOT gate, which was bias, which had bias noise, okay, where the Z errors only propagated as Z errors. So now we simulate the XZX lattice for different size of the lattice, so 9 by 9 to 21 by 21. And so this is 9 by 9, 13 by 13, 17 by 17, 21 by 21. And all these lines for the logical error rate as a function of the total gate infidelity cut at a single point, which tells you that's the threshold, that's the point of threshold. Now we do the same simulation, but now replace the bias noise control NOT gate with the unbiased case, where the Z errors are converted to Z and Y errors. In that case, we get this and we get the threshold here. You can clearly see that the threshold here is about 2% and here it's about 1.6%. So there is a difference in the threshold. You did get a bigger improvement in the threshold when you had the bias noise control NOT gate. More important is the logical error rate. So say you had two types of systems in which the total gate infidelity was the same. So say I took the total gate infidelity to be 1.4% here. But in one case, the gate infidelity, the gate was so that the noise in the gate is biased, but in the other case, the noise in the gate is not biased. Clearly, for the total infidelity, the logical error probability for the biased gate is lower, orders of magnitude lower than the logical error rate when I don't have that bias noise gate. Even though the total infidelity is the same. The only thing that has changed in the two cases is where these errors happen, and just that made a big difference in the total logical error rate by orders of magnitude. So this really tells you that it's important to have a bias noise gate, and this comes to my points to the first message that I was trying to say, which was that know your noise and fidelity should not be the only metric, and you should also look at the structure of noise. Okay. So now what we, with these promising results, what we wanted to do was build the XZX code with now our Kirkat qubits, because as I mentioned earlier, with these Kirkat qubits, I did have this CNOT gate with bias noise, and I could not have that with regular qubits. And what we find is that indeed you can get large improvements in the threshold for the bias noise gates, and this is only possible because we were utilizing this continuous variable nature of our Kirkat qubit. So this is a theorist imagination of what the XZX surface code with the Kirkats might look like. So now these circles are replaced by your snail qubits, snail mons, I don't know what to call them. And so you have the purple ones, which are the data snail mons or snail cats, and the green ones are the ancilla snail cats. And you could imagine a 3D connectivity where you can control each of them individually. Okay, please don't take that circuit too seriously. So now what we do is we take our Kirkat system, we set some parameters of the system. So we say, we fix the current nonlinearity that we can have, and then we vary the quality factor, if you might want to say, or the lifetime of the snail. So basically we changed this ratio kappa, which is the single photon loss rate, divided by the curve. Now we fix the thermal photons. So we add thermal photons and we fix it to 6%. This is also at a the thermal photons is 6%. So this is also at a high, or this is also a pessimistic account of the thermal photons. We don't expect them to be this high, but what if they were this high? Do we still get an improvement? And so now, by fixing these parameters, we also now make the Kerkat in it. So the plot that I'm going to show you is for the Kerkat with size 6 photons, which roughly corresponds to about a bias of 2000. And what we do is, again, simulate the XZX lattice and look at the logical error probability. But now this time, the noise we put for the different gates comes from my master equation simulations for these different parameters of the Kerkat. So this is truly, a realistic simulation that we're doing. And so for the same parameters, we simulate, the control not gate measurements, readout, control Z gates, take those numbers and put it in our XZX lattice and see how the code does. And again, we look at the logical error rate for different sizes of the lattice. They all cross at one point, and that is the threshold. And so we expect the threshold at this point. Well, what does that point mean? It means that, say I have a Kerr nonlinearity of about 10 megahertz, which is what they have in the experiment currently, then at this point would correspond to a kappa over Kerr of about 2.5 times 10 to the minus 4, which means 1 over kappa, or lifetime, or bare T1 time of the snail to be 64 microseconds. Now in current experiments, this quantity is about 15 microseconds, so it's not too far away from 64 microseconds. We can surely reach there. Now, to give you a little bit more intuitive sense, on the top axis here, I'm also plotting the corresponding gate infidelity. So this point actually corresponds to a gate infidelity of about, about 6-7%. So that means that now the threshold infidelity for your gate operation is about 6%, which is much higher than 1% of the regular surface code. So this is a huge improvement that we have got here. So now this comes to my second message, which is that fault tolerance with bosonic codes is not only possible, but it is more practical. You can make it much more efficient. Okay, so all this hinges on the fact that we have this bias noise C0 gate. So Nick is doing this experiment now, and hopefully we'll see results soon. So I'm going to stop here with the two main messages, and also tell you that we have ongoing work to improve other aspects of the surface code, such as magic state injection and distillation. And we have some preliminary results which show that you can also improve these guys quadratically, like you can reduce the overheads for distillation quadratically if you have bias noise qubits and gates. So I'm going to stop here and take questions.
Thank you, Shruti. Are there questions? Or maybe as people think about their questions, I can ask one. So you mentioned that the number in the previous slide was 64 microseconds is what you were kind of hoping for, or at least better than that to be on threshold. But that sounds a little bit pessimistic for any superconducting device now. So is there some particular problems with the snail mon, or
what do you mean by pessimistic?
That's, well, the 64 microsecond is very short. You would expect to be able to do much better now with.
But that's the point, like, so that's the whole point, that even with a much lossier cavity, you can still be below the threshold.
Right. Okay. So you expect that you'll beat this like by a lot.
Yeah.
Considering that transmons have 100 microseconds.
Yeah.
Right?
Yeah. So this is threshold. So of course, if you have a better cavity than this, then you'll be, like here or down here somewhere. So that is obviously excellent, but basically the point is like how bad can you make your system be and still be able to
okay. So okay. Another question? Yes, Joachim, you can unmute yourself.
Hi, thanks for the talk. Very nice. Yeah, why? First, a small question. Why the green curve? The larger lattice seems to be performing in a poorer way as the 17 by 17 at the very low.
So it's not actually. So I apologize. So here the error bars are really large.
Right, okay.
I forgot to. So just a few days back, I redid this like at this region and reduced the error bars a lot. So it doesn't actually. Yeah, it is still below the orange line. So I just forgot to change the plot.
Okay, thanks.
Yeah.
And if you go back one slide, maybe. No, one side again. Yes, so this plot, I was wondering if you had a. This is all simulations, right? It's not. You don't have a. And if you had like a formula that quantifies exactly the threshold as a function of the bias, or.
Oh, so you mean the actual threshold as a function of the bias?
Yeah.
Oh no, so I don't have that, but for the XZZX code, it tends to follow the hashing bound. So you can use that. I mean, okay. So if you had a perfect decoder, then you would actually it'll be exactly equal to the hashing bound, right? But it's not. So it's obviously below the hashing bound, but the sort of the shape looks similar to that of the hashing bound. So if you want a rough formula, you can use that.
Okay, thank you.
No problem.
So there's a question in the chat. Who is thanking you for the nice talk, who says, since the X error is unlikely to happen, how do we see the radializations of Kirk-Cat in the double well picture? So how do you control the qubit? About that,
right. So that's related to this point. So you can do an X gate if you wanted to, but you are right that because of the double well is preventing you from doing any X. So if you want to do an X, if you want to do Rabi oscillations with respect to X, then you have to cut off the double well, basically kill it by removing your 2-photon drive, and then do just a free evolution under Kerr, and you'll be able to do this. So in our surface code, we will when we do logical operations, we will actually never do this X pi over 2 gate on our physical qubits, because for that we need to destroy the bias, which we don't want to. But it turns out that you don't need that gate. You don't need that gate at the physical level to do a universal, to build a universal gate set at the logical level. So at the logical level, we'll only use initialization. So when we build the surface code, we'll do all the gate operations using lattice surgery, which only requires initializations, the C0 gates, and measurements. And then for the magic state injection and distillation process, we'll use these gates. But other than that, on the data qubits, we will actually never do an X pi over 2 gate. That's a good question, and that's an important point.
Thanks. Is there another question? Yes, Julien.
Hi, Shruti. Thank you for your talk. I'm just wondering if you have any comments on this XZZX code versus the one that the Paris guys are pursuing with the repetition cat code. Is there any advantages for the surface code, or so what's the pros and cons of these two codes?
Well, the surface, as I said, in the infinite bias limit, the surface code is a repetition code. So if you have infinite bias, or biases like 10 to the minus 12, which is what the Paris guys are looking at, then yes, you can work with the repetition code. But if you believe you can achieve 10 to the minus 12 bias, then for sure go for it. But to me, getting a bias of 10 to the minus 12 is as realistic or unrealistic as making a Majorana fermion. So pick your poison. So to me, like to me as a theorist, sorry.
Can we quote you on this? No.
Sorry, yeah, so to me that's unphysical. So to me, this lattice is better because you have protection against the other errors as well. So this works even if I have biases of 100 or 1,000 or 10,000, which is to me like 10,000 is like approaching, you know, the hard limit. So that is a difference. The question is, yes, if you have really large biases, then yes, go for the repetition code. If not, then I would say go for the XZX code. Now again, it depends on what you want to do. If you want to use the code for say running Shor's algorithm or something like that, then you need to be at the fault tolerance level. So you need error rates of 10 to the minus 12 to 10 to the minus 18, right? So in that case, then you do need, if you just want to use a repetition code, then you need the bias of like 10 to the 12 or something like that. But if you just want to make, say reach break even or something like that, if you just want to show some, a small quantum memory just for, near-term applications, then you might get away with repetition code even with smaller biases. But for fault tolerance, I don't think that's going to work.
Okay, thank you for your answer.
No problem. So there's actually a modification of the XZX code, which is even closer to the repetition code. It's actually a rectangular version of the XZX code. And there basically, one side of the rectangle is the Z repetition code and the other side of the rectangle is like the X repetition code. So if there are no X errors, just remove that. You just have a 1 by L surface code, which is the repetition code.
So is there an optimal in the asymmetry between the X and Z direction of the codes, or it's
yes,
unknown
so we
at
are
the
working
moment?
on that. Yeah, so depending on the bias, you might want to choose what is the X height and the Z length, I guess. And so wait for a month more and you'll see results.
Thank you.
Okay, do we have the question maybe? I wanted to ask you about AP versus this, but maybe this is something we can do offline. Probably some people want to go for lunch now. Oh, Danny has one. Okay, Danny, quick one.
Yeah, quick one.
Hi,
sorry.
Danny.
So just do you have any comment about let's say using a simple transmon versus using a snail-based transmon? So I guess the efficiency of this 2-photon drive is better for a snail-based transmon, but then the lifetime is worse. So do you have any comment
I'm
on
not
this?
sure. Well, I'm not sure if the lifetime is worse. Honestly, again, lifetime is not the only thing that matters, right? What matters is the gate time divided by the lifetime. So if you just look at the absolute gate fidelities that they have, it's like close to 99% in the first experiment where they didn't even make any effort to make a good qubit. So I don't think that lifetime by itself, it should be the sole metric again. That being said, there are problems with driving transmon. So when you apply these two drives, firstly it limits the limits on which how hard you can drive, because what happens is that I can't remember which one, but one of the red or the blue detune one, I always get confused between the signs, but one of them actually can cause accidental transitions to other levels, which can be a problem. So if you drive too much, you can do bad things to that, which doesn't happen as much in the snail case. The other thing is that in the Kerr case, so in the regular transmon case, this P, how much you can drive, is this P is directly proportional to the Kerr nonlinearity. Whereas in this case, in the snail case, this P is unrelated or not directly related to the Kerr nonlinearity. So you can independently increase P without affecting the Kerr, whereas in this case that doesn't happen. So you have sort of more freedom in your driving parameters in the snail than this case.
Thanks.
No problem. But that being said, I don't know, like there might be, so when they were trying the first experiment, they did try this technique and it wasn't, working very well. So they went to this guy and then it just worked. So, I think in the beginning, they're going to stick to this. But that being said, there's no hard and fast rules that this is not going to work. I think it's just a question of fabrication and, more intelligent design, I guess.
Okay, thanks.
Great. Thank you. Thank you very much, Shruti, for the great talk and for answering all of these questions. Thank you, everyone, for joining us. So I guess if you have more questions for Shruti, you can also catch her at the BBQ workshop, which she is co-organizing later this week. I don't know if this is open to everyone, but I imagine on Zoom it should be fine to have more people. So there will be more talks on that type of. I think you're giving a talk.
Yeah, and I'm going to talk about the magic state work there. So.
Magic state. Okay, excellent. And there's a talk from Nick Fatini also on the experiment. So if you want to have updates there. Right, so this is a very exciting direction. For sure, there'll be more work coming in that direction from your group, the group at Yale, and elsewhere. So thank you again for taking the time to talk to us. Very nice seeing you again, and see you soon, I hope.
Thank you. Thank you so much. It was great to hear from everybody.
Yes, well, it was good to see. There was more people than the last few weeks, than the last several weeks. So you succeeded in attracting more people. Thank you for that, of bringing more people together. So that's great.
Great. Is this? Am I still sharing, or what's happening? I can't tell.
No.
Okay.
Now it's not sharing anymore.
Okay, great.
Lots of thank yous.
Okay.
Okay, well.
Thank you.
Thank you again. See you very
Thank you.
soon, and
Yeah.
I guess I'll see you online this week.
Yeah, great.
Bye.
Bye-bye.